Hello everybody, welcome to Pre-Calc Lesson 12.11, Graphing Rational Functions. So this is like the culmination of everything that we've done in this unit. I'm going to give you a rational expression and you need to graph it without the use of a calculator. Well, as you can see here, there are several steps to doing this and it kind of seems daunting, but once we kind of go through a couple examples, I think you'll see the flow is just kind of natural once you have an understanding of what we're trying to do with limits. So the first thing we're going to do here in step one, determine what the domain is, right? Find where it has discontinuity. Well, if you remember, a function has discontinuity wherever the denominator is equal to 0. So the first thing I like to do, find where it has discontinuity. Set that denominator equal to 0, find that x value or x values. Okay, so next, we have to determine the type or types of discontinuity. So if I give you a rational expression, it's either going to be point discontinuity or it's going to be infinite discontinuity. So we're either going to have a hole in the function or we're going to have a vertical asymptote. Now, this is where it gets a little bit confusing, but what we have to do there is we have to take the limit at all of our places of discontinuity. If the limit exists, so like the limit of f of x as x approaches 2 is 7, that means there's going to be a hole in the function, because the limit exists, but the function doesn't. If the limit does not exist, that means we're going to have a vertical asymptote at that x value. Okay, so after we do that, we find the limit as x approaches infinity. Now what that's going to do is that's going to determine where we have any horizontal asymptotes. So in the last lesson, we found how to take the limit as x approaches infinity. It's pretty straightforward, doesn't take more than a few seconds. But what that limit tells us is if and where I should say, we have a horizontal asymptote. Okay, next, this goes back to what we've done earlier in the year. We have to find the intercepts. We have to find the roots and the Y-intercept. So for roots, if you remember, to determine where we have roots, you have to set the numerator equal to 0. Now, up above, when we take the limit, we have to simplify the expression. So you set the numerator equal to 0 of the simplified expression. I'll just put f of x. Now, where do we get the y-intercept? We get the y-intercept, if you remember, by setting x equal to 0. And then whatever's left over for our y value, that's the y-intercept. Just a quick note here, remember if 0 is a root, that's also your y-intercept. You don't need to go any further. So next we want to determine, does the function have symmetry? Again, if you remember back to the very beginning of the unit, we talked about an even function versus an odd function. And what you can do here, because we're not proving, we just want to determine, is if you plug in f of 2, and then you plug in f of negative 2, and those two are equal, we say the function is even. If you remember, an even function has symmetry with respect to the y-axis. If you evaluate f of 2 and f of negative 2, and you get opposite values, like 5 and negative 5, we say the function is odd. And remember, an odd function has symmetry with respect to the origin. And then the last thing we're going to do here is we're going to find other points if necessary. Sometimes after we go through steps 1 through 5, there's still not enough information to make an accurate graph, so then we're just going to plug in some value of x, like f of 6, if we need something on that side of our axes. All right, let's take a look at an example. And again, I kind of like to go through this in the same sort of progression. I think it's very helpful for you guys to do the same thing, because once you do something a few times, that repetition kind of kicks in. So the first thing we always do when it comes to graphing a rational expression is find where it has discontinuity, denominator equal to 0. All right, so I'm going to take a look at this, and I'm going to say right away, well, I have discontinuity at x equals 1, because if I plug in a 1 for x, that function's undefined. So now, once I know where I have discontinuity, the very next thing I like to do is take the limit as x approaches that value. Okay, well, I'm going to take the limit of f of x. If you notice here, I can't do anything with this. I have to use direct substitution. I can't simplify this at all. So if I plug in a 1, I get 2 over 1 minus 1, which is 2 over 0, which means that does not exist. So what do we have there? The function has discontinuity. The limit does not exist. That means I have a vertical asymptote at x equals 1. And that's a super important concept. So if you want, you can actually throw this into the graph right now. Let me pick a different color. At x equals 1, I know I'm going to have a vertical asymptote. Don't know anything else about the graph at this point other than that's a vertical asymptote. Okay, so now what do I do? Well, let's go back here. Found, did this, took the limit there, got my vertical asymptote. Now I take the limit as x approaches infinity. Okay, so I take the limit as x approaches infinity of this expression. Well, if you remember from the last lesson, this limit depends on either the numerator or denominator having a higher degree. So in this case, my higher degree is in the denominator. So you can kind of think of this as all the other stuff going away, and I've got x in the denominator. So this is going to be something over infinity, which means that's 0. So if your limit to infinity is 0, that means I have a horizontal asymptote at y equals 0. So now if you want, you can put this in the graph. Y equals 0 is simply the x-axis. There's my horizontal asymptote. Okay, so now what? Now I need to get roots, and I need to get y-intercepts. Well, you can probably guess now, I'm not going to have any roots, right? Because my x-axis is an asymptote. But remember what you do for roots is you set numerator equal to 0. Well, that's not going to do anything for us here because notice there's no variable there. That's just a 1. Right, I should look up here. That's just a 2. Okay, so there's no roots. All right, so now I want my y-intercept. So for my y-intercept, what do? Well, I set x equal to 0, and I write down what's left. So I have y equals 2 over 0 minus 1, 2 over negative 1. So my y-intercept is going to be negative 2. Well, that's kind of helpful because now I know at negative 2, my graph crosses the y-axis. So the next thing we're going to do here is determine whether we have an even or an odd or neither in terms of our symmetry. So there's a couple ways you can go about doing this. I know right now I don't have either one. I can tell that just from the graph because I know it's impossible for my graph with the asymptotes the way they are to have symmetry with respect to the y-axis or the origin. But let me just remind you guys how to do this algebraically. I'm going to plug in 2 to my original function. So I come up to my original function, I plug in 2, I get 2 over 2 minus 1, well that's 2. Then I plug in a negative 2. So that's going to be 2 over negative 2 minus 1. Well, that's negative 2/3. So they're not equal. They're not opposites. No symmetry. Now, I generally only do this if the question specifically asks for symmetry, in which case you have to show this work. But if the directions simply say graph and show all steps, you don't necessarily have to show this because it should be obvious when you're done with your graph whether it's even or odd or neither. So what do I know here? On this graph, I have enough information to get the piece that ends up being in the lower left quadrant. I know I have an asymptote here, I have an asymptote here, and it has to go through this point. So I know I have something that kind of looks like this. So I'm going to sketch that in right now. All right, that's going to go that way, and that's going to go that way. So this is a great example of I don't have enough information to finish the graph because I don't know what's going on over here. I know there can't be anything here, right? Because if I put something up here, it's not going to be a function that's going to fail the vertical line test. So I know there's nothing here. But there could be a piece here, or there could be a piece here. How do you know? Well, all you have to do is plug in any point for x that's over on this side. So I see a 2 here. I think that's probably going to be the easiest. I like small numbers. So what I'm going to do now is I'm going to evaluate the function at 2. Okay, so if you remember, there's my original function. And actually, thinking about it now, you've already done that, haven't you? Check this out. So I know that that is equal to 2. So I've got this point right here, 2, 2. Once again, this piece is going to be easy to sketch because I know that's an asymptote, I know that's an asymptote, and it's got to go through here. So I'm looking at something that looks like that. All right, so let's sketch that in. And there we go. We've graphed this rational expression, and I've shown all the steps here. Our second example is probably what I would call test level, if you will. This is about as challenging as it's going to get, because if you notice here, your denominator is a little bit more involved than our last one. So the first thing we always do, take a look at that denominator, set it equal to 0, because that's going to determine where we have discontinuity. Well, before I do that, I want to factor this. All right, so I think if I factor that quickly, I got x plus 3 times x plus 4. Now, do not cancel. You have to determine where you have discontinuity first. So I'm going to have discontinuity at x equals -3 and x equals -4. You have to get this before you take the limits, before you simplify the expression. So now, since I know I have discontinuity in 2 places, I'm going to find 2 limits. One limit's going to be as x approaches -3. I'll find that in a second. The other one's going to be as x approaches -4. So I kind of like to set that up before I simplify. So now I know direct substitution is not going to work. So let's just cancel what we can here. I see this x plus 4, that x plus 4, those are going to cancel. So what am I left with? I'm left with this expression 1 over x plus 3. So 1 over x plus 3 is going to go here, and 1 over x plus 3 is going to go here. So now in this limit, if I plug in a -3 there, guess what? I get 1 over 0. So that does not exist. So remember what we said. Our function has discontinuity at -3. The limit does not exist. So what does that tell me? That tells me I have a vertical asymptote at x equals -3. Okay, so -3 on the graph, I have a vertical asymptote, which is similar to the example we just did. But now check this out. For this one, if I plug in a -4, I get 1 over -4 plus 3, 1 over -1, that's -1. So now what this tells me is I have discontinuity, but the limit exists. So if you think back to types of discontinuity, that's going to be point discontinuity. All right, so graphically, that tells me I have a hole in the function at -4, -1. All right, so -4, -1, there's a hole in the function. So on the graph, I'm going to put an open circle on that coordinate. Okay, so next, after you take the limit at the places of discontinuity, now I'm going to take the limit as x approaches infinity. And one of the things that I like to mention, once you've simplified this expression right here, I probably should have written that down, but once you've simplified this to find the limits, you can use this for the entire rest of the problem. When it comes to roots, Y-intercept, symmetry, whatever you want, this will work. Just make sure that you find this here first before you do any simplifying. Find where you have discontinuity. Okay, so having said that, let's find our limit as x approaches infinity. I've got 1 over x plus 3, and remember how we do that. I've got x in the bottom, so you can kind of think of this as 1 over infinity, so that's going to be 0. The limit as x approaches infinity gives us a horizontal asymptote at y equals 0. So similar to the last problem, I have this. Now, we're just sketching here, all right? So since we're sketching, take a look at our lower left quadrant, if you will. That's an asymptote. That's an asymptote. It's got to go through that, but not contain it, remember? So I'm going to have something that looks like this. Open circle, approaches that asymptote, and approaches this asymptote here. But that's an open circle, remember, because our function has discontinuity there. Okay, so now, again, symmetry. I know I don't have symmetry. I know I don't have roots, right? You already know you don't have roots because this is an asymptote. So it's not going to cross that. But a y-intercept. A y-intercept is going to tell me whether my function is up here like this or whether my function is down here like that. Remember, it can't be here, right? You can't have one above the other because that's not a function. So let's just find our y-intercept. So y-intercept, I'm going to set x equal to 0 in my simplified expression right here. Okay, so it's going to be 1 over 0 plus 3. Oops, sorry. Or 1/3. So my y-intercept is 1/3. I know, again, we're just making sketches here. I know that's not ideal, but it's going to go through right there. And since we're just making sketches, and once again, you know, this is an asymptote here, that's an asymptote there, it's got to go through this point. Remember, it contains that point. It's going to look like this. Okay, so there's a fairly accurate sketch of this rational function using limits, places of discontinuity, and finding roots in y-intercept as needed. Our final example we'll talk about in this video lesson, f of x equals 4x squared minus 3x over 2x squared. Okay, so I want to graph this rational expression. Denominator equal to 0 to find where it has discontinuity. So 2x squared equals 0. I know I'm going to have discontinuity when x is equal to 0. Okay, so after you determine all the places where you have discontinuity, the next thing you're going to do is take the limit there. The limit as x approaches 0 of this expression. Well, right away I know direct substitution is not going to work, so let me take a second to clean this up. If you look at this numerator here, looks like all we can do is take out a GCF. Okay, so if I do that, I'm going to take out an x. I've got 4x minus 3. In my denominator, I've got 2x squared. So what I can do is just cancel those. That leaves me 4x minus 3 over 2x. Okay, so I'll go in here. 4x minus 3 over 2x. Well, when I plug in a 0, you can see here, I'm still going to get a 0 in that denominator. So even though I've simplified this as much as I can, that limit is still going to be something over 0. So that limit does not exist. So remember what we said. I have discontinuity. The limit does not exist. That basically means I'm going to have something that might look like that, a vertical asymptote. So that gives me a vertical asymptote at x equals 0. So graphically, you can put that in right now. X equals 0, vertical asymptote. Okay, so now what do? Now I'm going to take the limit as x approaches infinity. Limit as x approaches infinity. Again, I'm going to use this simplified expression, 4x minus 3 over 2x. Okay, so what I want to do now is I want to focus on the exponents of x. First degree, they're equal. The degree of the numerator and the degree of the denominator are equal. So basically what's going to happen here when I take my limit as x goes to infinity is I'm just going to be left with the ratio of those coefficients. All right, so it's going to be 4 over 2 over 2. So what we're saying here visually, as x goes to infinity, the y value is going to approach 2. So that becomes a horizontal asymptote. Horizontal asymptote at y equals 2. So again, graphically, I can put that in. All right, so what do we do now? Well, now I need to find some roots. I'm pretty confident in this case I am going to have roots because notice that's not a horizontal asymptote. So how do we get our roots? We're going to set our numerator equal to 0. All right, so that's the numerator of the simplified expression. That's 4x minus 3 equals 0. So I get 4x equals 3, x equals 3/4. All right, so that is a root. That's a point on the function. X equals 3/4. I know it's going to be kind of small. I apologize for that. So I've got that root right there. So now, without doing anything else, I'm going to need to do more. But right now, I can get a piece of this graph because notice I have an asymptote here. I have an asymptote here. The function has to go through that point. So I'm going to have something that kind of looks like this. All right, so let's put that in. That's a horizontal asymptote there. And this is going to get closer and closer that way. Okay, so now what I need to do is I need to figure out, because I know, again, can't have anything here. I can either have something here or possibly something here. So you can try and find a y-intercept, but if you notice here, this is an asymptote, so I'm not going to have a y-intercept. If I set all my x is equal to 0, you get something that's undefined, so no y-intercept. So what I'm going to do next is I have to find another point. I have to plug in one of these x coordinates over here to determine, let's say I'm going to use -2. I want to determine if my point is down here, in which case I have something that looks like this, or if my point's up here, in which case I have something that looks like that. Okay, so what I'm going to do next is plug in f of -2. Okay, so I've got 4 times -2 minus 3 over 2 times -2. Let's see, that's -8 minus 3, that's -11. And that's going to be -4, so I have 11/4, which is, what, approximately 2.75? So basically all you need to know, again, we're just making sketches, is that when x is -2, y is almost 3. -2, almost 3. It's going to be right there. So I have enough information now to create a rough sketch, because remember, those are asymptotes, and that's what that function is going to look like. Now, if the question specifically asks you for symmetry, I could plug in a 2, f of 2, and determine if they're equal or opposite or neither. But this is why I said earlier, you can take a look at your picture right now, and you can determine there is no symmetry. There's no symmetry with respect to the y-axis, and there's no symmetry with respect to the origin. All right, anytime you've got a horizontal asymptote that's above or below the x-axis, you can't have symmetry with respect to the origin. And obviously they're not images of each other with a reflection in the y-axis. Okay, so again, I apologize for the long video. I know this is a lot thrown at you. Our next day of notes is basically more of this, so you have some more time to kind of let it sink in. Again, please reach out if you have any questions, and thanks for following along.